a real treat tonight for you. We have Mr. Greg Snyder from the Harvard-Smithsonian Center for Astrophysics. Greg is currently very close to getting his PhD and has graciously volunteered to talk to us about his research that he's doing in preparation for his final dissertation and PhD award. So I'll also mention we've also had some other speakers in the past here from the same organization. So it's great that we're able to bring folks back like Greg and other folks and colleagues of his that you'll be seeing in the future. So thank you, and with that, Mr. Greg Snyder. Thanks.
Testing. Is it working? Great. Okay, thanks, Rich. Thanks for having me here. So I'm not very experienced talking about my own research to the public, so please bear with me. So I'm going to talk to you today about galaxies, and in particular, so here's an admission I have to make, is that I have not looked through a telescope in more than 5 years. So most of my work is theoretical in nature, and I use supercomputers to simulate the formation of galaxies, and I'll tell you what that means throughout the course of my talk. So the punchline, or the motivation for all of this is I want to understand why galaxies appear the way they do. And here are just two examples of galaxies. On the left is a spiral galaxy, much like we might expect our own Milky Way to look like. And on the right is a so-called elliptical galaxy that's rounder, has fewer features in it than do spirals. And so I want to understand all the things that fit into this blank here. So it's a fill-in-the-blank problem. And sort of anything that has to do with setting this sentence is what my research is focusing on. So what sets galaxy appearance? So in the first part of my talk, I'm going to talk a little bit about what galaxies are, what is in them, what are the important processes that act on galaxies, and then the tools that we use to try and understand them better. So I thought I'd start small. So here's a mock-up of the solar system, not to scale, obviously, but here we are on planet Earth. And then if you take our solar system and shrink it down, and imagine it inside a galaxy. So this is the definition of a galaxy, essentially. It's a big disk of stars that are all rotating around in a self-gravitating way. And so this will take several 100 million years to rotate in this pattern. But if you take the entire solar system and shrink it down, it'll fit in less than a pixel. Can't even see it on this image. Yes, a question?
So which way does that galaxy rotate? Like a pinwheel or the...
I have no idea.
Do we know which way the arms go?
Yes.
We get a blue shift.
Yes, yeah, there are spectra of these galaxies, but for this one, I don't know. But, right, so you can see our solar system is really just a speck in this whole grand design spiral. And now, I have a little bit of a demonstration to get started, just to set the scales here. So I want you to imagine that this yellow foam ball is the sun. All right, so if this is the size of the sun, then where do you think the Earth would be? Where?
Elm Street.
93.
Not quite that far.
93
So
diameters of that ball in whatever
roughly,
direction.
yeah. So this is a few centimeters across. So the Earth would be a meter or two away. So the Earth would be out here. It'd be very small. You couldn't really see it, but it would be, within arm's reach. And so now my second question is, so there are a lot of stars in the galaxy, stars similar to our sun. How close would the nearest star be if this were the sun?
Next town.
Next town? Concord? Boston? The moon?
Is it 6 trillion miles?
Okay, so lots of guesses. It turns out it would be roughly Buffalo, New York, is where the nearest star would be.
A lot of space.
So there's a crap load of space in between these stars.
And it's only a pixel.
And it's only a pixel on this image. Okay, so that's the thing. The stars in galaxies are really far apart. So this is really, really big compared to a solar system. And now, of course, we don't see our galaxy that we live in from this perspective. We're actually embedded in the disk. So what we see on a nice dark sky is something like that, which is an image I've never really seen in person, but is what it looks like from inside the disk. And I see this glow of stars in edge-on fashion. Now, there are many other galaxies in the universe. We're not the only galaxy. And here's a diagram of the observable universe through an astronomical survey, where now instead of each point or pixel being a star, each point or pixel is an entire galaxy filled with trillions of stars. And so now our galaxy is just a tiny, tiny point looking outward from the center.
We're right in the middle.
Yeah,
How can
I
that
always
be?
knew that was true.
right in the middle.
We
But-
are the center of the universe.
So now,
The camera.
there are now observed billions of galaxies in these surveys, each with trillions of stars. And now let's do my same experiment again, where if this quarter is the disk of our Milky Way galaxy, how close do you think the next large galaxy is?
Just a couple
That's where your hand was.
California?
Well, next galaxy, Andromeda is not that far away if you're talking about that.
So some of you know the answer already, and it's about that far. So if this is the size of our galaxy, the nearest galaxy is, relatively speaking, compared to the stars, extremely, extremely close. So the takeaway message, and if there's one thing that you should learn from this talk, is that compared to their size, galaxies are really close together. And what that means is that galaxies can collide, and stars cannot. So their stars are so far apart that when they're rotating around in the galaxy, they will virtually never touch each other. They will never collide. But galaxies are close enough, only a foot or two on this scale, that they interact and collide during the course of the universe.
Well, all those naughty sections have been clumping together since the beginning of the universe.
Exactly.
That's why there's more interactions, probably.
Stars have gravity too, but but yes, yeah, they've had a lot of time to do
When the
their
galaxies
business.
collide, the stars don't either.
Right,
Pass by.
exactly. So I'm just going to dim the lights now for the rest.
Here we go.
We like darkness.
Going dark.
Dark.
So this universe that we're observing, we've put together a story over the last couple of decades of how it all came to be. And that's what I've heard termed the double dark theory, where most of the universe is composed of so-called dark matter and dark energy. So dark matter is sort of anything that gravitates, so it has gravity, but we can't see it or can't observe it in any way except for gravity. And dark energy is even weirder in that it can only be observed by the very large scale stretching of the space between galaxies. And so in this theory, galaxies are really just along for the ride, where the dark matter is dominating the gravitating mass of the galaxies. And you can see here we are, atoms, and the stars that you actually observe are only 4.5 or 5% of the total matter in the universe. And so the galaxies are just along for the ride. The gravity brings the structures of dark matter together, and the galaxies come with it. And the cosmic expansion of dark energy moves the collapsing structures apart. And I won't really get into that for the rest of the talk, but this is the sort of background for galaxies.
What's the other 0.4%?
Us.
No.
Luminous.
That's a good question. I don't know.
Very
Dark energy.
I have to look into
Off
it.
error.
It's all price.
Round
Yeah.
off error.
Muons. It's random muons. Jeez.
Yeah. So with this backdrop, now we can understand what we're looking at when we look at the sky and we see galaxies. So this is one of the deepest exposures of the sky ever made by humans. It is the Hubble Ultra Deep Field. So it's from a space telescope, and it was over the course of several months in 2004 that this picture was made, or set of pictures was made. And there's over 11 days of continuous exposure that went into this picture, and over 800 individual frames were taken. But what you can see are actually maybe 1 or 2 stars, individual stars in this picture. The rest are 10,000 galaxies on the sky. And so, yeah, I think that's pretty amazing. And what you can see about the galaxies is that they come in many different shapes and sizes. So as I mentioned before, there are these elliptical fuzzy galaxies, the red ones. There are the spiral-ish galaxies, the bluish ones here. And sort of everything in between. And we want to understand why. And so a basic trend that we've uncovered is that if you go from now and into the past and look at galaxies, so we can do this because the more distant galaxies, their light takes time to get to us. And so if a galaxy is extremely far away, we're actually seeing it as it was billions of years ago. And so the faint fuzzies here are from the light we're seeing is from billions of years ago. So we're seeing those galaxies as they existed in the very distant past. And so we can put together a diagram like this one and say that, okay, the faint fuzzy things in the very distant past, billions of years ago, looked like this. Now they look like this. And there are a couple, and the main thing that happens is galaxies grow in brightness from bottom to top. So from the past to now, they've gotten bigger. The bigger ones have gotten brighter, I should say. And they're also more unusually shaped in the past. So they're not as round, they're not as disk-like in the past as they are now. So here again is just the same thing in pictures. Our Milky Way, we believe, is a spiral galaxy. There are many others that are ellipticals, and we're trying to understand why is there this difference in the way they appear, because this is not predicted by the dark matter theory. So the evolution of the dark matter does not tell you that you should get two different kinds of galaxies at the end, but we do, so why? So, yeah, so the basic difference between spiral galaxies on the right now, elliptical galaxies on the left, is that the spiral galaxies are bluer on average than the elliptical galaxies. And they're bluer because they have young stars, which are hotter than the old stars. And so the fact that they have young stars means, sort of trivially, that they have stars that are continually being formed. So in these galaxies, there are stars that are newer. And the elliptical galaxies, they must be older because there aren't any young hot stars there. So there are many things that can act in galaxies, and I mentioned star formation as one of them, and I'll explain that a little bit more in more detail. Black holes can affect the appearance of galaxies, and also galaxy mergers, which is what I'll be focusing the rest of my talk on. So star formation is an extremely complicated process. So here's our solar system on the bottom right. Eventually, our star will run out of gas or run out of fuel, and it'll stop burning hydrogen in its center. And when that happens, it can't support itself anymore. And it'll shed its outer envelope into space. And this is, I label star recycling. So it puts all of the material back into interstellar space, which that material, again, will collapse and form dark clouds and form stars later. And so this process is kind of a cycle where the material that forms in stars is then expelled back out into the galaxy and then forms stars later again.
Each time with less and less hydrogen, I would assume.
Yes. So in the center of every galaxy, we believe there is a supermassive black hole. And that's shown here in kind of a cartoon form, where here's a galaxy, and in the very center is a black hole, which has an extreme amount of gravity and sits at the bottom of the gravity of the galaxy. So everything that comes near the center of the black hole gets funneled to the center. And when this material that was spewed out by stars, this, I call it gas, but it's a mixture of gas and dust and other particles, it gets heated to extreme levels. And that when it's heated, it radiates in extreme ways. And so this is seen here in jets that are coming out of the galaxy. So these are extremely energetic events that launch this material that used to be in stars and was recycled out of stars, out into intergalactic space, and removing it from the galaxy entirely. So this material is then no longer available to form more stars. And so you can imagine that if this black hole is extremely active for an extremely long period of time, it could remove all of the gas from the galaxy and totally halt star formation altogether. And so this is a theory that has been put forward as to explain why there are these galaxies with no ongoing star formation. Is that all of the gas was funneled near the center or was heated by the black hole in these extreme events and is no longer forming new stars. And then galaxy mergers. And so here's a couple of beautiful pictures demonstrating that galaxies do in fact collide, like I told you. And you can see how messy this becomes. And so that's really the takeaway of this slide, is that both of these processes depend on this gas and stars being churned up in some way. And mergers are one way to do that. And so if you take two galaxies, smash them together, you can see them getting torn apart. And you can see, and there'll be some better images later on, but you can see that the material that's inside them gets sort of jumbled up and mixed up, and the processes like star formation and black hole energetic events can be triggered in that way. So here's our two quarters on the screen, the Milky Way galaxy where we reside, and the nearest large disk spiral, the Andromeda galaxy on the right. And I just wanted to demonstrate what's going to happen to us. So here's what the night sky will look like in the next couple of billion years. And so the Milky Way and Andromeda are slowly moving towards each other. In a couple of billion years, we'll merge, just like the images I showed you, and the sky will be spectacular.
Can't wait.
I'll mark my calendar.
Oh, my camera still works then.
Yeah,
Would it be too bright to observe at that point?
good question.
That was awesome.
And so this now goes back, this is going backwards, and it's going to go forward again.
Brings visual observing to a new meaning to the word visual observing.
So, yeah, this started really fast, but here's the Andromeda galaxy, which you can see is a sort of faint fuzzy now, and there's the Milky Way spiral disk. But then, as time moves forward, it gets brighter in the sky, and then the two galaxies eventually get warped and twisted to see this magnificent star formation. See, these red things are triggered star formation events. So this star recycling and star formation events occurring in the new galaxy.
Well, because of what you said earlier, there's really no like devastation.
Yeah.
Well,
Sorry, there's a question here?
Yeah, well, just a point you had mentioned that the stars don't collide,
Yeah.
but the dust does.
The dust and gas absolutely collides. Yeah.
and the other thing that happens, unfortunately, Rich, is not going to be a good story for us. All the junk, everything, there's a lot of gravitational interactions, and loose bits and pieces in the Oort cloud and the like will come raining in on the inner system.
Yeah.
We don't have to worry about it tonight.
So there'll be a lot of comets.
And
There we go.
Is
Yeah.
Andromeda coming towards us, or are we coming towards Andromeda? Whose fault is it?
I have a question, Greg.
Yes.
If space is expanding, does that make it more difficult for the galaxies to come together?
It does in general. So if you take any two galaxies, they're less likely to collide because space is expanding, or the universe is expanding. But Milky Way and Andromeda are so close to one another that their mutual gravity dominates over the cosmic expansion.
Right.
And so they're so much more massive than the force pulling them apart. That,
Isn't the
they will-
expansion mainly the voids between the galaxies that's expanding?
That's right.
Local group.
So here's just another gratuitous picture of a galaxy merger from NASA, from the Hubble Space Telescope. And you can see again these dark dust lanes, gas and dust, being funneled to the center of this galaxy after an interaction, triggers star formation in the outskirts, and so on. Okay, so what does this mean for our question? So we just learned a little bit about what can change galaxy appearance, what can trigger star formation, what mergers do. All of these things are involved, but they must be disentangled in order to truly to answer this question for any given galaxy. And to do that, we have to become sort of archaeologists in some way. So all we have is one sky. We can't watch the galaxies themselves evolve over time because it takes billions of years for them to do so. And so instead what we see is galaxies at different distances and how their general statistics and populations evolve. And so it's a bit like archaeology where you can see a skeleton from millions of years ago and you might be able to say a little bit about how it lived, but you can't say exactly how it lived. You can't know exactly what caused it to be the way it is. And you also can't tell how it evolved in the future. And it's the same way with galaxies. You have to sort of piece together this story from indirect ways. And so we can't observe galaxies over time, and we need some way to link them together. And so that's the goal. We want to be able to make a universe from scratch. So here's a sort of schematic of the evolution of galaxies. Here is the Hubble Space Telescope, which I've been featuring a lot on the left in a cartoon fashion. It sees all these galaxies close to us. And in the distant past, say 10 billion years ago or so, galaxies were much smaller and more irregular. And before then, they were just a few stars. There was nothing really to them. The first stars were formed. And in the very beginning of the universe, things were much smoother. And so the so-called Big Bang and afterglow of the Big Bang that we can observe in other ways. But we want to understand, can we take what we know about the beginnings of the universe and evolve it forward in time using equations to get out this picture of galaxies in the end. And so far, that has been impossible to do in science, but our research is trying to do that. And so we want to try and simulate 13.8 billion years in computers to try and get galaxies out at the end. And so here's just an example movie of a computation. So this is taking bits of dark matter and seeding them in the way we think the universe started, so after the Big Bang, and just watching what happens according to the laws of gravity. And so it's a little pixelated, I apologize for that, but what you can see is structures of dark matter starting to form and collapse into bigger structures. So things start very smooth, but then become more inhomogeneous as time goes on. And so this is sort of the filamentary web of matter, and galaxies are going to be forming in sort of the nodes of all of this web. However, this is just the dark matter. We don't have any stars or gas or any of that fun stuff that I was showing you during the mergers here. This is just how the matter evolves. And so this is just taking... Yeah, sorry, there were a question?
This is very well developed for only half a giga-year. Is that how things really happened? Did it develop? Did the structure develop that quickly?
Yes, in some systems.
Quickly.
Yeah, so the structure formation occurs in what's called a hierarchical manner, in that the small things form first, and then bigger things form later. So what we were seeing at the beginning of the universe, a giga-year, a billion years into the universe, is just a small galaxy that formed. But the larger galaxies, like the Milky Way and clusters of galaxies, will then form much later.
But the filaments, I mean, they were very well pronounced after only 0.1 giga-years.
Yeah. So that is when the structure started to collapse.
Wow. Okay.
Yeah.
There's like quite a mess going on here.
Yeah. So that's an interesting point. It's messy. It's not a thing that you can write down on a piece of paper and explain how the gravity evolves in these systems. You have to store all this bits of information in your computer and let it do the calculations for you, which is how this.
This hasn't been zooming while it's been doing this, has it? It's been staying at a fixed distance, I take it?
I'm actually not sure.
It's zooming in because that 500 kiloparsec thing was a lot
Oh,
smaller.
that Z on the upper left is the zoom?
Oh,
No, ignore that.
Okay.
They said 500 kiloparsecs on the bottom.
Yeah. So I'm not sure if it's zooming or not, but sorry, question in the back?
How much computation time did this take?
This one I'm not sure. I didn't do it, but I will have one later that I'll mention how many resources it took.
It's rotating too.
Yeah.
That's just so we can see it as a 3D.
Yeah.
Oh.
Rich, did you have a question?
Yeah, so there's mathematical equations behind this.
Yeah.
So those are theorized.
Yes.
The best guess is, okay, we can represent what we think happened by these mathematical equations. The simulation crunches the numbers into those equations and produces this.
Exactly.
So I mean, how do you try to prove that then? Do you try to prove it through observation then at some point?
Yes. Yeah. So that's really the punchline actually, is that So we have this ability to perform these equations in computers. How do we now go and check that we have the right theories? And that's really hard to do, especially. This is not what you observe in the universe. You see the luminous stars and galaxies, not the dark matter. So the dark matter is really, really easy to simulate because it's just gravity. But it's the other things I talked about, the black holes, the star formation, the mergers between galaxies, that we can't do as well. And so that's what we need to work on.
Can you just start from the present and go backwards, or is that not possible?
That's right.
That's not how he's doing it.
No, I don't think
That
anyone's
wouldn't
done
test
that.
that wouldn't test the computation, because what you're looking for is you're going to come up with this computation and see if the real snapshot matches what you end up with.
Exactly.
Now.
Yeah.
And you can only do that now because you have powerful computers that can process these complex equations that you derive.
Yeah. So the dark matter calculation that I just showed you was something that could be done on a medium-sized computer cluster of a few thousand computers 5 years ago or 10 years ago. Yeah. This is a computer that I've used. This is called the Odyssey cluster. It's in Boston. This is actually how it was in 2008. It's actually like 5 times bigger now. But this was 5,000 computers housed in a room in Boston. And this is what I've been using for the last 5 years of my dissertation research.
Is there a bunch of NVIDIA graphic cards in there, or are they using?
No, they're 8-core Intel CPUs.
It's a bunch of blades, right?
I was just
Yeah.
saying, there are IBM blades.
Yeah.
It's all computation, there's no video coming out.
So have you ever thought about
Yeah,
doing
the
what SETI's
computation is
doing?
the video.
And enlist
In video.
everybody in the world's computer to compute,
Yes, but with the kinds of calculations that form galaxies, they all need to communicate with each other. So you can't, in some sense, you can spawn them off into different people's computers,
Right.
but in many of the cases, they're all coupled.
5
You
cents per
can't.
minute.
That's why
Yeah.
they're in a cluster like that, because they're covering the shared memory.
Exactly, yeah. So they're all big memory pipes between all these things that make this possible. And on the bottom is a newer machine that I've started using in San Diego called the Gordon Flash Supercomputer, and it's got solid state memory, solid state hard drives to make the reading and writing of data much simpler.
it's faster.
Yeah, orders of magnitude.
Yeah. So we basically just talked about everything that I put on this slide, is that we're trying to translate the theories that underlie the equations of gravity, gas dynamics, and star formation, and black hole growth into mock reality. So we're trying to produce something that looks as realistic as possible, and in practice, it doesn't look realistic, so we want to understand why. And so the two critical elements that I'll talk about next are things that I've mentioned a little bit. Merger rates, so the rates at which galaxies collide, and black hole growth. And so these are two areas that are related, and which have gotten a lot of attention in the research community lately. And the supercomputer simulations have given us a lot of new information in these areas, and I'll try to explain that. So this is also something that we mentioned briefly. The technique that we use is fairly straightforward as far as what you're trying to do. You're trying to solve equations, and you want to try and solve the equations as best you can. And the way researchers do this is to try and discretize space. So break space into pieces that are easier to understand. And so here's our galaxy. It's got stars, it's got gas and dust, and it's got a black hole probably over there in the center. But you want to try and break it into pieces that are individually easier to understand. So if you then break it into a grid like this one, you can then solve the equations only across boundaries here, as opposed to on the galaxy as a whole. And so then in this way, you can move the equations forward in time and get a picture for how the galaxy evolves. And now the challenge with this is that everyone argues over how small a box you need. So how good is good enough for solving the equations of gas dynamics and gravity in a galaxy? How much precision do you want? Do you want things at the scale of the solar system? Do you want to form planets in your galaxy simulation, or do you want to just form clumps, spiral arms? Is spiral arms enough for you? And then relatedly, do we understand physics well enough to say that we understand how stars form in these pockets? So can we write down an equation that we think mimics reality in the right way in a single one of these boxes? And that's sort of the argument among researchers.
I've always heard if you do simulations of a known beginning that you can go away, you can get array real quickly. It can become a mess real quickly.
That's exactly right.
How do you dampen that so that doesn't?
There's the whole area of numerical analysis, which is another problem that you have, as well as the sort of chaos type thing that you've been talking about is diverging from the real path. But every time you do one of these iterations, you introduce a problem because the math you're working is working with finite, like floating point numbers, and you wind up with like half a bit of error after every computation you do. And if you do that computation 100 million times, the error term creeps up into your entire number.
So double precision would not be enough. You didn't have more.
Yeah. So at the point of numerical precision in hardware, our knowledge of physics is not good enough for this to matter.
Oh.
So the equations are uncertain at such a level that the numerical imprecision that you mentioned, or the chaos that you mentioned, is not the dominant factor anymore.
But you're importing nonsense bits into this as you relax the grid.
True. Yeah.
The small errors actually may produce the turbulence you need to make all these cool things appear.
Only just the right kind of error.
Otherwise, you'd be just
No, actually, so this is actually exactly what we talk about in group meetings. So this is you guys hit the nail on the head here. But I'm going to move on now because this we will be here for hours. So the challenges are essentially twofold. One is that you need a huge dynamic range. So you want to be able to get all the way across this galaxy, which I said is filled with space, lots and lots of space. But you also want to be able to model things like dust clouds and star formation in the galaxy. So you need things that can understand physics on small scales and enough calculations that you know how to put it all together on big scales. So that's what I mean by huge dynamic range. And the physics are extremely complicated, and I just mentioned this, that we don't really know the equation that takes you from here to here very well. We have to model it. We have to make it up, essentially, and then test it and see how well we do. And so any one of these steps is highly uncertain, and so we don't really know the right answer. And so researchers have been refining this for decades now, and here's a recent one this is a snapshot of a supercomputer simulation of two galaxies merging. On the left is gas, which is not really what I've been showing in the pictures. But on the right is sort of a mock-up or mock image of what you would expect the merging galaxies to look like. And I would say that we're getting pretty darn close. So we have things that look like star clusters forming in the outskirts of the galaxies. We have these streamers of gas and dust evolving. And so this is now an extremely, extremely intensive simulation with maybe tens of billions of individual particles that were evolved over the course of 2 or 3 billion years. And so this is my field of research, is mock observations. So taking one of these supercomputer simulations and then trying to predict how it would appear in the telescope to astronomers. And so this is essentially what we do, is we take all of our knowledge about the stars, the gas, and the dust, which comes out of the computer as a prediction of someone's model. Now, it may not be a very good model, but we take it for what it is. And then we propagate radiation through the galaxy in such a way that we then have what we believe is a realistic image at the telescope or at our observations. And so this takes into account different wavelengths of light. So you can have visible light that's propagating from stars. You can have the visible light that is absorbed by the gas and the dust, which is then heated from this energy, and then it emits its own infrared radiation. And so all of these processes are taken into account in our work, where we take the predictions from the supercomputers and try and make an image in the end, or a spectrum, as the case may be. So here's an example of starting from a simulation and then trying to make an image. Just a galaxy merger. And the camera moves around a lot in this one, so I'm sorry if you get dizzy.
They must have said. Look at the blue stuff. Ooh.
Yep.
Those are all the blue
A lot of
stars.
blue star formation. Yeah.
What are those white things running around there? Is that part of a core of another?
Yeah, those are really dense clusters of stars. And so you can also see sort of, yeah,
Oh, that's
the dark stuff coming in between the galaxies. That's dust that's obscuring the light from the stars.
How much matter do you think you lose from the stars that get ejected?
I don't have a good answer to that. Probably a few percent in collision like this.
If these were just intact stars in a system interacting, wouldn't they just, if it had a escape velocity of one galaxy, wouldn't it just keep going and pass along through? Why does it come back after the first interaction?
There are equivalent of frictional
Because the
losses.
gas absorption stalls it?
No, it's a gravitational friction actually. So it's as a star passes through a group of other stars, it feels the gravity along its entire path, and so then it'll get slowed down and then come back to the center of the whole system. And so the galaxies exchange this energy as they interact.
Each orbit gets closer and closer until it's merged.
Yeah. So galaxies are extremely efficient at doing this, and they'll if they get close enough, they'll almost certainly do a final merger.
But we do have images of galaxies where they have clearly interacted and have gone on, and they are not going to come back together again.
That's true. So it all depends on the relative velocities, and all the situation is that the universe was seeded very randomly. So there's sort of all sorts of things that can happen. This is just one out of billions of examples of what can happen when galaxies interact.
So it looks like this made an elliptical galaxy.
Yes. Yeah. So this is for a long time mergers have been the sort of not necessarily smoking gun, but the sort of best estimate we have for why some galaxies are elliptical and others are not. Some galaxies undergo these mergers that form ellipticals.
So that means there should be no old ellipticals.
Right. So there should be no, well,
Ellipticals are old.
the stars are old, but they may have formed recently.
Okay.
But not, the galaxy may have become elliptical recently.
I see.
Would a lot have to do with the spins, you know, because if you've got them coming at different angles?
Yes, so that, yeah. So there are some mergers that form spiral, for example.
Well, we know the Milky Way has absorbed a number of dwarf galaxies and remained spirals.
True.
How many stars were in this simulation, if they were stars?
I'm not entirely sure. This one is probably
Count the dots.
this one is probably 1 billion points that were simulated, but I don't know the number for sure.
Wait, let it
Yeah.
come together again.
So I'm just going to show this one more time because I want to point out one thing at the end.
We love watching it.
Black
Yeah.
holes are merging as well during this, right?
And so at the very end, it rotates around the elliptical remnant,
Right.
and you can see this dust lane appear. I may have just missed it, but
There's two.
yeah, there it is. So there's
There's two components, two spiral components, it looks like.
Yep. Different angles.
And we see that in actual mergers.
that's right. So this is looks very much like some of the images of the galaxies I showed you before. And I think it's going to do this on purpose again. Yeah,
I don't like
the dust
it.
lane.
Yeah.
So it's a, yeah.
It's cool.
Centaurus A.
Still
Yep.
dim.
Okay, so that's a galaxy merger. What we want to understand how galaxies built up over time. Mergers are a very critical element of that because you double the mass in a one-to-one merger. You add mass every time you have a merger, and this is sort of telling you that you build up this mass as we showed in the trends. But it's a really hard thing to measure the rate of galaxy mergers, and the reason is as follows. They look really messy. And so it's really hard to understand what you see. And so I read an analogy for this this week, actually, that looking for galaxy mergers by looking for pairs of galaxies is a bit like counting fender benders when you see them happening, which is a really hard thing to do. I don't know if I've ever seen a fender bender happen on the highway in person, but I've seen dents, and I've seen people tell me afterward that oh, I had a fender bender today, or something like that. But I've never actually seen them collide on the highway. And so in the past, astronomers have estimated merger rates by looking for pairs and saying, oh, there are 1% of galaxies are in pairs, so the merger rate is something like 1% in some amount of time. But in truth, mergers leave all kinds of disturbances and other things that are harder to get at in the data. They're not as obvious as pairs. There are these dents. There are these stories that the galaxies that have that astronomers can then look for. And so these detailed disturbances were made mostly with the Hubble Space Telescope. So this is a telescope that is outside the atmosphere and has enough sensitivity to see these fine features on the outskirts of the faint fuzzies. And this now is theory. These are images made from my simulations. In the bottom is sort of a mock-up of visible light images. And you can see this is just a time series in a merger. So the galaxies collided, like I showed you in the movie, and then just evolved as a remnant. If you look at the left, they're a pair. There are two galaxies there, roughly speaking. Then the rest of it's just one. You might say this is an elliptical galaxy already, especially if you don't have very high resolution like the Hubble Space Telescope. You say, oh, that's just a round galaxy. There's no merger there. That's just a round galaxy. There's no merger there. And that's just a round galaxy. There's no merger there. But in reality, all of these are evidence that there was a merger. And so when I started my research, this was the first project I worked on, and that is looking for these detailed disturbances in the stellar populations of the galaxies. So the stars contains signatures of their formation history based on how old the stars are and how massive they are. So these merger remnants, when they form stars in this fashion, this sort of bursts of star formation that I showed, they retain this imprint of young stars for a long period of time afterward. And in particular, there's a kind of star that's very obvious in galaxy spectra. So here I show a spectrum of a galaxy, or a model galaxy. So this is light flux on the y-axis, wavelength of light on the x-axis. And so blue colors are on the left, red colors are on the right. And stars that form in a starburst, or really young stars go through a period of time where they're so-called A stars. And this is just jargon for having these really sharp and strong hydrogen absorption features in their atmospheres. And so some of you may recognize this as the Balmer series of hydrogen absorption, so H alpha, H beta, H gamma, H delta. And these features are extremely strong in stars that are approximately 1 billion years old. And so if you have these whopping features, it means your galaxy is dominated by stars that are about 1 billion years old. And so something happened 1 billion years ago to form those stars. And that is the galaxy merger. And so we can back out from the spectrum of galaxies what happened in the past to form all these stars. And so this is one of those detailed disturbances that I mentioned. Instead of seeing a pair here, you see just sort of a blob. But in the spectrum, there's this remnant of star formation. And so this is sort of what my observatory looks like. It's an image of a fake galaxy that I made in a computer. And here's sort of an aperture that I put down and measure the spectrum of here. And so it's just an example of one of our simulations. And you can see here the Balmer series of absorption lines and then emission lines, actually, in this particular part of the galaxy. And so these emission and absorption features in a spectrum are something that physicists have been using for a really long time to learn things about matter. And in particular, the chemistry and radiation of gas, or radiation inside a gas, can be probed from these lines. And so here's just a spectrum of an astronomical so-called quasar, but just something in space. And you can see labels on here with different elements and chemical labels. And so these can, by measuring the relative strengths of these, you can tell something about what's happening in the system. And in particular, I mentioned that black holes can emit extreme radiation at the centers of galaxies. And when something like that happens, this signature is very obvious. So a black hole will accrete some matter. It'll dump an extreme amount of radiation into the center of a galaxy. And that radiation will change the emission spectrum that you see from the galaxy. And so the signature becomes extremely obvious compared to just normal galaxies that are just sitting idly by. And so why do we care about these black holes? Well, I mentioned they could impart enough energy to unbind the gas entirely and halt the star formation in the galaxies. And that's what's happening in this simulation. So it's a merger. We're looking at gas now and not stars. But seated in the center is a massive black hole. And you can see puffs of, looks like smoke, but it's just gas being puffed out by this intense radiation. I think it gets better.
But if all this gas is leaving the galaxy, wouldn't it collect on another galaxy nearby later? It's not really lost, right?
Yes, there you see a giant puff of green smoke and more as the gas from the center is driven out by this radiation. So back to your question, the gas will leave the galaxy or go up into the atmosphere of the galaxy, but it may be heated to such a temperature that it can no longer efficiently cool back onto the galaxy. And so it may just take too long for it to form in another galaxy. So galaxies take some time to collect their gas, and it may just be too slow.
High temperature, but very diffuse.
Yeah, exactly. And so this means it's important for us to try and understand the impact of these black holes on the gas and dust in the galaxies. And this is another project I worked on. So here's a galaxy spectrum again, with flux on the y-axis and wavelength on the x-axis, and this is now in microns, so we're now off into the infrared. But the black hole dumps enough energy that it heats up the dust that's in the galaxy to an enormously high temperature relative to what it normally is. And so this dust then radiates extra infrared light. So much like a heated oven or something will glow red, the dust will glow in infrared from this energy. And so we can then trace back, looking at a source. Here's a model source from 7 billion years ago. We can then analyze the spectrum in this way and try and understand how much energy the black hole is dumping into the surroundings by making these mock infrared images of galaxies and try and understand their energy content. And in particular, this is something that I'm particularly excited about from the James Webb Space Telescope. So this is the successor to the Hubble Space Telescope, which will hopefully be launched by the end of this decade. And this is a 6.5 meter aperture. Here is just a computer image of it. It's a 6.5 beryllium-plated mirrors, 6.5 meter beryllium-plated mirrors, and a sun shield, which looks kind of fun on the bottom. And then this will be launched hopefully by the end of the decade. Costs NASA $8 to $10 billion. So this is going to be the most expensive astronomical project in history, perhaps more than many others combined. And it will allow us to measure the infrared light in this area of the spectrum more sensitively than any other astronomical instrument.
This one won't be at a serviceable altitude, correct?
Correct.
This is
We'll
going
build
to
it
be way
up.
It's going to be at the L2 point, I believe. For those of you who know what that is.
What can
I'm not sure what the launcher is, but I think they have it already.
That's a big telescope.
Yeah, yeah. So I should have had an animation of this thing. In order to launch something with 6.5 meter aperture, they have to fold it up into the rocket. So instead of launching, like the Hubble Space Telescope went up in a shuttle, it could just sit in the cargo bay of the shuttle. The James Webb Space Telescope is going to be like a hermit crab inside one of these rockets, and then it'll just unfold once it gets to its destination. Hopefully. There are many people working on making sure that it unfolds correctly. And so in the last few minutes, I want to expand on this a little bit because I've shown you simulated galaxies, one or two of them at a time. But in the last 2 or 3 years, it's become possible to model significant fractions of the entire universe at a single time, or in a single computation. So when I started my PhD, we were talking about individual galaxies. There's no way you can simulate the gas, dust, black holes in galaxies in hundreds or thousands of galaxies at a time. But fortunately, that has changed with the increase in computational power available to astronomers, and maybe just their ability to use it, perhaps. So the last thing I want to talk about is, so here's again the Hubble Ultra Deep Field, and we want to see if we can make fake pictures of it, or make it from scratch. So now the methods we believe we trust to a high enough degree of accuracy that we can expend significant amounts of computational resources in addition to telescope resources studying these issues. And this is a supercomputer in France called Curie. And the group that I'm associated with recently got allocated 45 million CPU hours on this machine and is currently running a single computation of the universe from the beginning. So it's about halfway done and will be done in May or so.
How long is a CPU hour in real hours?
How many CPU hours per hour of wall clock time?
So it's taking about 3 months total.
Okay.
So I have to write it down.
How many processors? Right?
Yeah, and it's something like 8,000 processors.
8,000. Yeah, that sounds right.
Nice. I want one.
Me too. And so the technique that made this possible by a guy named Volker Springel was instead of breaking the grid into square points, he now has his grid be sort of arbitrary tessellation of space. And this allows you to more accurately write down the equations of hydrodynamics and trace them without all the errors that I mentioned before, without the numerical round-off errors, or with smaller numerical round-off errors.
So when there's less going on, you make them larger tessellations.
Exactly, and you can adapt the size of them, but you can also have them move with the fluid. So instead of having a fixed grid of things that you solve the equations on, you're now solving the equations on a 3D arbitrary mesh that rotates around with the galaxy. So that's just a fun point.
Must have interesting state variables.
Yeah. And so here's a quick movie by my collaborators showing hundreds of galaxies at a time being simulated. And this is just the gas, not the stars. So Hubble, when I show you the ultra deep field, you're seeing mostly stars. This is mostly gas. And so here's a galaxy forming out of nothing, basically, or out of smooth gas in the universe. And you can see in the background all kinds of things happening. Galaxies colliding, galaxies interacting, things like that. More. I think this one has a merger at some point.
There was one going on in the background a minute ago.
Yeah. Let's see what happens. There's one.
that is processing all these interactions equally, so you can have different views of this movie if you
Yeah.
want to look at a
That's
different
right.
area.
Kind of, right? Very
Triple
good.
merger. You don't have to run
Yeah.
the process again.
That's right.
Teacup. Yeah.
Oh, just lost that one.
So someone mentioned before, this is pretty messy. Yeah, this is pretty messy, and it's the universe we live in, and it's hard to model, but we're getting close.
Reminds me of Frank.
So then, the thing that I've been working on lately is then slicing this up and trying to make how this universe would look from a given point, or from a galaxy as we observe it. So taking instead of seeing this camera moving around arbitrarily in space, how would our galaxies actually look in a telescope? And here's an example. The top is real data, an image from the ultra deep field, and the bottom is one of these simulations. They're in the same color bands, the same filters, the same units, same flux units. And so you now can compare directly in units of images rather than units of, say, just star formation or galaxy masses or things like that. You can directly compare them one to one and subtract them and see how different they are. In this case, they're pretty different. So this one seems to have some differences. It's brighter. There are more small blue things around than the real universe. And that's the function of our understanding of physics, is that in this case, we don't include processes that are significant enough or correct enough to give us the real universe. And so what my collaborators have been doing is trying to refine those models. And so here's another set of assumptions. You just change your equations, basically, and run it again. And it looks a little bit closer. And so it's still not quite right. You can see it's clumpier than the real thing. That's just because this is a low resolution simulation. And you can also see that it's bluer still a little bit. There aren't these isolated red galaxies in this image.
You got pink galaxies. I don't know if that's good.
I think that's what they are. Yeah, they're galaxies with both red and blue in them, where those don't exactly appear in the real universe. But if you then turn the knob a little bit further, you can start to get these isolated, really deep red objects, the red elliptical galaxies. And so that's this point we're at. We're starting to form realistic populations of galaxies that look kind of like the real thing, and there will be more coming off of the supercomputers in the near future for us to analyze. And so now we can take the universe as it would be observed in a telescope, and if we get the right answer, roughly speaking, we can evolve it forward and backward in time and understand how the galaxies evolved from one observed epoch to another observed epoch, roughly speaking, from the simulations. So here's just how Hubble would see a galaxy form and interact with its surroundings in an image. Sorry it's so jumpy.
How often do you get data from that simulation that you're running?
So it's going to have once a day, roughly, but it dumps something like 2 terabytes a day of data.
Do they email it to you?
Not exactly. So we're getting close to being able to make realistic images of the universe and hopefully in the near future understand what it means for the physics of galaxy formation. So thank you. And sorry, there's a question here before I.
Sure. I get the impression that there's a successful simulation that gets you closer to the universe you see.
Yeah.
And there's other simulations that aren't successful. What knobs are you turning to try to get a successful simulation? Do you change the law of gravity, or you change the physics law, or what?
So gravity is pretty much set. We think we understand what gravity is doing, but we change the messy things that I talked about. So this is the star formation law and the black hole growth. So the sort of way that gas funnels onto a black hole is poorly understood. Okay. And so this is really a dynamic range problem, is that we can't model the gas flows on enough detail in large galaxies to get it onto the black hole directly.
In other words, it's how gas moves around that.
Basically, yeah. So we have knobs that we turn of, like, say stars form a little bit more efficiently or less efficiently than we thought. You can turn that up. Black holes accrete or spew more energy into the galaxies than we thought. And so then once we have those settings, it's then our job to understand what the heck they mean.
Now, your job is to try to figure out how to turn it on.
Yeah.
You
Yeah.
mentioned that you might start with a smooth set of gas and then
Yeah.
evolve forward in time, but inspired by the recent Planck results. If the gas was totally smooth, I assume nothing would happen going forward in time.
Be metastable.
Yeah, so Ted is referring to the Planck data release from yesterday, which showed an image of fluctuations in the early universe. So this is the gas at a very early time, about 100,000 years after the Big Bang. And you can see temperature fluctuations in the gas, and those are the things that seed the formation of these structures. But if it were completely smooth, yeah, nothing would happen.
So in your simulations, when you start with a smooth set of points,
So I meant
have to insert
smoother.
sort of-
Yeah, so it does include the perturbations
It
from
includes some initial-
the WMAP data in these
Random number
cases.
generators are being used here somewhere?
Yeah, that's right.
Just the computations, but they have a little non-smoothness to it. Maybe not enough to do anything, but
Yeah.
still.
I wonder if you just have to do it.
Yeah, so the numerical, so they think the fluctuations are at a bigger level than the numerics at this level, but
That's good.
yeah.
So apparently they're definitely on the grow up from the small size. About 10 years ago, some people were trying to run these on a theory that the largest structures formed first.
Yes.
Is this definite, or is this just, well, definite as you can be?
So it's a bit of a labeling challenge. So what maybe I was being a little fast and loose with what I talked about in a large structure, but it seems to be that star formation was very efficient in massive galaxies very early on in the universe, and so that's what these giant ellipticals are essentially. They formed very early, and now they're just aging stellar populations. But other galaxies like the disks sort of build up over time, and they form from smaller pieces in general. And so it just depends on what you're talking about in terms of a massive elliptical galaxy, a massive cluster.
No, I
or
was talking
something.
about, when we first started reading this, one hypothesis was you first form areas of mass concentration that will become superclusters.
Yeah.
And then that fractionates into areas of mass concentration that will become clusters of galaxies, which fractionate areas.
I see.
As opposed to a bottom-up approach,
Yeah.
which says first we just do we do stars, and then you get the little dwarf galaxies, and then those coalesce.
Yeah. So the answer to that conundrum is that it's generally that the smaller pieces collect first, but in areas that are highly overdense with respect to the rest of the universe, things happen much faster. So you still have this bottom-up, like small things forming big things, but it happens in a much quicker way in superclusters.
That sounds like large and small mass stars. The larger collection of dust produces a blue giant, but it builds up real fast, and the red dwarfs.
Exactly. Yeah. So it's
take a long time.
analogous.
A key part of your algorithm is going to be the formation of black holes. So how close are you with that?
Pretty far. So the black hole formation is a sort of best guess for when they might have formed.
At what point do you think they're forming? I mean,
Within the first billion years, the seeds of the massive black holes are formed.
You have to worry about divide by zero when you get near a black hole in your math.
Not exactly.
Infinite, nearly infinite.
Not quite.
black holes are not
The
singular.
Milky
Yes.
Way is,
Simulate.
we think the Milky Way is surrounded by this shell of globular clusters.
Yes.
These beautiful things that we look at all
Yeah.
the time. We think, I've heard people say that those are potentially the remnants of galaxies, the cores of ancient galaxies, what's left after the merger. Do your simulations shed any light as to whether that idea is more or less right?
Not yet. So the simulations that I've been working on aren't detailed enough to tell us whether that's true or not. And these simulations that sort of form things from the beginning aren't detailed enough in general to get that. So you have to start with some assumptions for an isolated galaxy, and it's just harder. But I think we'll probably be there in 5 years or less.
I assume these are like the state of the art in simulations at this point.
Yeah.
Like on cutting edge.
Yeah.
Leading edge.
Yeah.
I read somewhere that they found large galaxies a lot earlier than they expected to find them. Does that appear anywhere in your simulation, or is that something that you just don't worry about right now?
I actually don't know the answer to the first part, but it's something that I'm not worried about right now, because I think the simulations so far are still kind of tuned to the observations in some way, and so I wouldn't expect it to be very different than what's observed.
Well, that's an observation, which is why.
Yeah, exactly. I wouldn't expect it to be very different, but I also wouldn't expect that that means a whole lot yet, because these are still relatively small simulations. So I said hundreds or thousands of galaxies, maybe 10,000 galaxies at a time is what we're simulating now. The 45 million CPU hour run is 45 million, and so observations are probing sort of millions of galaxies at this point. And so it's hard to tell. Any other questions? I'd be happy to stick around and chat more with anyone who wants to talk about this or another astronomy topic. And thanks.
Guest speakers, we'd like to always give them a little token of our appreciation. So David bailed me out tonight by, actually we do have, so this is a combination laser pointer and pen that you can use in a night sky as well. So,
thanks a lot.
Thank you. Yeah, before we do that.